Thank you for inviting me to be here. It's a pleasure to speak with you today, and thank you for all the climate action work that you're doing. It's a real pleasure to see so many people here today. So again, my name is Nan Rosenbloom. I'm a scientist at NCAR, and I'm specifically a climate modeler. And I'm going to talk to you today about the current research in climate modeling, and specifically the modeling we do with the Community Earth System Model, the CESM model, which is NCAR's world-class model. It's one of 3 in the United States, and we think it's the best. But I'm not a climate modeler by training. I'm actually a geologist. But I got into modeling because when I was a graduate student here at CU, I built a computer model to do hill slope erosion. And I felt that that was so exciting to model the natural world and physical processes with numerical equations that when I was able to get a job at NCAR, I continued in this research. And I've worked with the land model, I've worked with the Paleo group, I've worked on a lot of different projects. And right now what I do is I specialize in sort of difficult simulations where I put the model components together in unique ways, and then I run these simulations. So I'll be talking today about why do we need to use climate models and what is a climate model. I'll specifically talk about the CESM model. I'll talk about how we test the models and how we know that we can trust them. I'll talk a little bit about the CMIP the project, and then I'll talk and show you some videos from the high-resolution version of CESM, which we use to look at specific climate events and specifically climate extremes. So first, I'm going to step back just a minute and talk about, and take a look at what we're simulating when we're simulating the climate model. One of the primary things that we're simulating, of course, is the greenhouse effect. And we have energy coming into the Earth from the sun. Some of it is absorbed, some of it is re-radiated back out to space. But much of it is absorbed in this thin layer of the atmosphere. This thin layer of the atmosphere is, of course, what makes life on Earth possible. And so we want greenhouse gases in the atmosphere to provide that layer of warmth, this little blanket that we around our small little planet. But it's an awfully thin layer, and we're putting an awful lot of extra CO2, extra greenhouse gas in that atmosphere. And we're thickening the blanket, and it's warming our planet, as we all know. So let's see what else. Let's see. One of the things I want to emphasize is that I'm specifically going to be talking about climate models as opposed to weather models. Weather models and climate models, of course, are related, but the timescales are quite different. And weather models are constantly, they're designed to tell you a forecast in a few days to up to a week's sort of forecast. And they're constantly being updated with the most recent atmospheric conditions so that you can know whether you have to bring your raincoat tomorrow or whether it's going to be a nice sunny day. On the other hand, climate models are started from our best idea of initial conditions, and then as they start integrating forward, they just run based on the model physics as we understand them. And they're not constantly brought back to some understood condition. They are running freely, and the properties that they are showing are the properties of the physics that we've written the code to represent. So we know that a lot of the excess heat that's being generated in the atmosphere, about 90% of it is 90% of the heat is going into the oceans. The oceans are also taking about 25% of the CO2 emissions. That's got its own problems. I'm not going to be specifically talking about oceans today, but it's important to know that the oceans are taking up a lot of the excess heat at the moment. Oh, sorry. Where is all the CO2 going? We can see that we can partition it. It's about 45% of it is going into the atmosphere, about 35% is going into the land surface, and about 25% is going into the oceans. But with all this additional greenhouse gases, we're warming our planet, as we all know, and we basically are running an uncontrolled experiment on this one planet that we have to experiment with. And so the idea of why do we use climate models is because we need to create virtual planets to better understand the what-ifs of what could happen with this climate experiment we're running. I mean, we could not, or we could, sort of wait and see what happens, but maybe a better idea would be to try to take the information that we have and understand what's going. Of course, it's a very complex system. So when we're using a climate model, we're trying to simulate processes that range from tens of kilometers, like big thunderstorms or mesoscale systems, hurricanes, all the way down to algae growth in the ocean or even small leaf growth in forests. So it's a very complex and highly difficult system to simulate. Again, why do we need to, what do we know about climate models and why are we using them? So they're an approximation of reality. We know that they're grounded in physics. We take the best understanding we have of the current state of physics and we put those into equations. We validate our climate models against observations, and then we use them to test our understanding of the physics that we've simulated and our understanding of the forcing that we've put to the model. So we're talking, in this virtual planet that we're creating, we use the Community Earth System model to simulate this. So you'll see on the upper right, this is sort of a simulation of how the grid, how a model gridded climate model is put together. So you can see it's broken down into individual cells. Those cells extend high into the atmosphere, and in the model version that I'm looking at, it's 30 levels into the atmosphere, and we also have ocean levels that go, I think, 60 levels into the ocean. So we have component models that simulate each of these model components. So the Earth System model, I should say, is really not just one big model. It's component models that are coupled together by what we call a coupler system. And the coupler allows all these component models to speak with each other. So if you are in atmosphere, flux, you talk to the coupler, and that flux goes to the ocean, and it goes to the land. And then all these components take what they're given, they do their physics with it, and they send information back, which goes back to the atmosphere. And every time that the model is iterating, these component models are talking to each other and updating their system. So we run on big supercomputers. Cheyenne is the big supercomputer that we use. It's situated up in Cheyenne. It's called Cheyenne. It's up in Wyoming at the NWSC. And let's see, what else do I want to say about this? It's basically a system of numerical equations. Some things are parameterized, but most things are run by equations. Of course, this is all an approximation because we can't simulate each individual leaf, so we're approximating different plant functional types is what we call them, different ways that different vegetation grows. So let's see, what else one thing I want to point out is in this cartoon at the bottom here, we can see the size of the bubble is related to the size of the model code that goes into representing that component. So this, the lines of code that go into this are like there's like a million lines of code in the CSM. It's written in Fortran, which feels a little old-fashioned perhaps, but most climate models are still written in Fortran. I'll say more about that in a second. But so you can see the atmosphere is huge, and you can understand why. The atmosphere is, of course, applied everywhere, whereas the land model is also pretty big, but we know that the ocean model is pretty big as well. But the atmosphere, of course, is needing to communicate with both the land and the ocean. It's the biggest component model. It's hard to see, but there's land ice and there's sea ice, and Bill will be talking about the land ice model when he speaks with you. Okay. So do models get it right? So we know that all the models are approximations. So it's not a question of whether they're right or wrong. But the question that we need to ask ourselves is, do we know more after we've used a climate model than we did before we started? And the answer is yes, because the models are pretty good at getting, they're pretty good at getting it right. And I'll show you that in a second. But here are some quotes that I like to think about. The first one says, all models are wrong, but some are useful. the purpose of models is not to fit the data, but to sharpen the questions. We learn oftentimes more what we don't know when things go wrong than when we do when things go right. And then the last one is particularly interesting. It says a theory has only the alternative of being right or wrong, but a model has a third possibility. It may be right, but irrelevant. So we may be modeling something and we think we're getting it right, but we're missing the bigger picture. We've gotten it right for the wrong reasons. So that's another question that we're always asking ourselves as modelers. And how do we validate a model? Well, we test it against observations. We know the models have skill. That's the metric that we use is whether they're skillful in reproducing observations. We can measure against present day observations and also against paleo records, which we get from ice cores and all sorts of paleo proxies. So up on the far left corner, you can see global surface temperature, and you can see the red line is the CESM2 model. And the blue line is another version of our CSM model. And the other lines, the black and the pink, those are all observations. And you can see we get it pretty well. On the x-axis across the bottom is time, so that's 1850 to 2000. We're doing pretty well. We don't get every detail. If you'll see close to, just after 2000 on the upper left, you'll see that the model is still going to the sky, but the observations have sort of leveled off. That's the hiatus period. We don't always catch every detail, and sometimes we don't understand why. There's people that are working on trying to understand that. But we do a pretty good job. We think that our models have skill because we can validate them against observations. We can also do hypothesis testing. And in these plots, what you see on the upper left is we force the model with only natural forcing. In other words, we've taken volcanoes, we've taken out the increase in greenhouse gas, basically. This is solar forcing, this is volcanoes, this is ozone, things like that. And we're forcing the model with that. And you can see that the observations are in red and the model is in blue. So the observations are heading up, right? They're increasing. But the model is not. So the model is not getting the full warming of the observations when we only force it with natural forcings. On the upper right, you can see the model when we only force it with anthropogenic forcing. So we're taking only the greenhouse gases and we're taking out anything else. It gets a lot closer. We're sort of mimicking observations, but only when we go to the bottom panel, where we have natural and anthropogenic forcing together, do we see that we match the observations the best. So in this, we understand that we can tease apart why our model is getting the right answer by taking these sensitivity tests and taking pieces away from the model and seeing what it does, and then putting them back in and getting a fuller picture. So the model allows us to look at possible scenarios because our model has what's called internal variability. And I want to show you this because it's a really interesting application. This is what was called the CESM large ensemble, or the lens experiment. And what these are is this is 30 representations of the same model simulation. Started at the same time and ran for 180 years. Each simulation started with the same forcing and was forced with the same forcing through this entire period, but each one was given a tiny, tiny, tiny perturbation at the beginning. So, 1 times 10 to the 14th, minus 14th, perturbation in the atmosphere. And you can see that we get really different results. What we're looking at in this image, the details aren't that important, but it's wintertime precipitation through the period of 2005 to 2060. So this is like a future period. And I've highlighted 2 different scenarios in the red boxes. On the top, you see this sort of red or dark blue, which means wetter than average precipitation in the southwest. And in the lower red box, I've highlighted an area where it's dry, 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 very arid for this 50-year average period. So the model, the same model forced with the same conditions, has produced very different model representations of what our future is. So this is sort of like, this is the variability we're looking at. We have, of course, our one experiment, but our virtual planet can tell us that there's more than one possibility. It's that butterfly effect that you've all heard about. So we know models help us to ask what-if questions, and we also know that models have strengths and weaknesses, and we only have one model it has its own strengths and weaknesses. So how do we choose? How do we know we've got the right model and that it's doing what we want it to do and that we can believe the results? So the Coupled Model Intercomparison Project, or CMIP-6, I'm sure you've heard of this. This is the sort of, this is the 6th phase of this project, and the results of this go into the assessment reports, which go to the IPCC, and those that go out to policymakers and inform climate policy. It's an international project. And we compare the results of many coupled models. There's over 40 models that participate in this climate assessment. And anyway, that's what we do. The model is forced, so these simulations are forced by what are called shared socioeconomic pathways. And if you were interested in the 5th assessment, they had RCPs, or the representative concentration pathways, I think, something like that. So these SSPs are related to RCPs, but they're slightly different. And on this figure, you can see that in very light gray, you can see that as you go higher on the plot, that has high challenges for mitigation, and lower on the plot are low challenges to mitigation. If you go to the left, you have low challenges to adaptation, and to the right, high challenges for adaptation. So the 2 plots on the top are sort of more severe scenarios. There's going to be more warming in those, and they're hard to read. So in this next plot, we'll look at the SSP1, which was in the lower left corner, was sustainability. It's basically taking the green road, so it's low challenge to mitigation and adaptation. The one in the middle, if I go back for just a sec, the one in the middle was the middle of the road, and that has medium challenges to mitigation and adaptation. The third one has regional rivalry. That's a rocky road. That would be high challenges to mitigation and adaptation. That's sort of a worst case scenario. Inequality is SSP4. It's of divided roads. It'd be more challenging to adapt, but mitigation might be better. And fossil fuel development is SSP5. Again, these were all put together with the idea that there are choices that would be made in policies that would lead to different outcomes. And so this is sort of a representation of what that would look like temperature-wise. If you can see right about here, this is now. And the things I want to point out, this is 21st century, and climate models typically run the future out to 2100. And the colors indicate red for getting much hotter. And the numbers, which are too small for you to see, are listed on those things. And the top number says 5.1 degrees C, global warming. And the bottom one is 1.3 degrees C. Now, these are all different pathways based on those SSPs and RCPs, those storylines that I pointed out. But the thing I want you to notice on this is those little triangles. Those are the peak emissions. And so for the bottommost strand of this little figure, where it says 1.3 degrees C warming that we're committed to, we'd already have had to have peak emissions. So this is a really hard thing it's hard to see how we're going to move forward on this, but one of the things that we'd have to have done is already had peak emissions. Then there's other pieces of this plot that are really interesting, and I'm happy to share this if you have any questions about it. So that was about CMIP-6. I just want to touch a little bit on the high-resolution model, the high-resolution version of CESM, because this is the model that we use to look at extreme climate events. And it's a high-resolution model, meaning that our grid cells are smaller, and we output much higher frequency. So if before most of our output was on monthly or maximum daily basis, now we're putting it out at 3-hourly or 6-hourly and sometimes even hourly basis variables so that we can understand exactly what's happening. The things that we are simulating with this high-resolution CESM model are extreme precipitation events, atmospheric rivers, there's Pineapple Express, the things that come in and hit California. And then, oh, thank you. What's that? Okay. And then we have hurricanes and tropical storms. So we all know that a warmer atmosphere holds more moisture, and we've seen that most recently in in Tropical Storm Imelda, where we had over 43 inches of rain. We remember the floods in 2013. Now, not a single event can be attributed to climate change exactly, but we know that with a warmer atmosphere, we're more likely to have more severe storms, or the storms that we have will be more severe and they will have more rainfall attached to them. We see this is a single frame from a climate simulation. The top is the present day and the bottom is the future, and the bright colors in the bottom are representing the precipitable water in the atmosphere column, and we have more precipitable water in the future climate simulation than in the past. So these are just my last couple slides, but I wanted to show that this is the kind of simulation that we get out of a high-resolution model. So what we're looking at is tropical storms hitting the Gulf of Mexico. They're just kind of propagating, and then up the eastern seaboard you can see, I think, you can see Florida here, and you see storms coming in and working up, and this high granularity of these high-resolution models teaches us a lot about the model and also about the effects that we can expect. We can take this into a global framework. I think this is going to work. And what this is I mentioned earlier that this is a community model, so these are some of our colleagues from another institution, and they're running this coupled model at high resolution ocean as well. And they're looking at those were little tropical storms going across the Pacific, and now they're able to turn the model on its side, and we're looking to see what effect that's having at the deep ocean. Of course, when you get a tropical cyclone going across, you're mixing things up, and what you're doing is you're mixing the warmer water down and you're bringing the cooler water up. So what you're seeing is the cool wake of these tropical cyclones as they zip along the ocean. Pretty cool stuff, I think. Let's see. So the one caveat with this, high-resolution simulations are very expensive, and they require large allocations on high-performance computers. So we need to partner with many institutions. I personally run jobs on HPCs or high-performance compute centers all over the country. And now our latest work is we've been partnering internationally with a group from China, in Qingdao. So this is with an ultra-high resolution ocean. This is a 10th degree ocean. You can see the ocean currents moving across the, moving across the equator. You can see on the most, you can see the climate or the seasons changing from north to south and south to north in the Arctic. So this is a very expensive model. And I remember telling you in the beginning that the CSM model is written in Fortran. Well, one of the things that they did here in China is they've rewritten it in C. So that, I think, is the first time I've heard of that ever being done. Just kind of interesting. They have many, many, many more people working on their model than we do. So we're helping them get set up, and then hopefully we'll get some information back from them as well. And that's all I had, and I would take any questions, but maybe we'll go Bill first.
Yeah, maybe while we get Bill to help us have.
Thank you very much for the invitation. So I'm going to talk about glaciers and mostly ice sheets and their effect on rising sea levels, which I'm sure you've heard about. Global average sea level was pretty flat for about the last 2,000 years or so, but around the start of the Industrial Revolution in the late 1800s, started ticking up. And during the 20th century, you had a sort of slow, steady increase in sea level. And then starting around 1993, which is when we became able to measure sea level by satellites, by measuring small changes in the surface elevation of the ocean, we've had a more detailed record. And since then, we've seen an acceleration of sea level. Sea level is now rising by a little more than 3 millimeters per year, which averages out to about a foot over a century. But that increase has been accelerating. Current sea level rise, there's two main contributors. One is melting of land ice in the form of ice sheets and glaciers. That contributes about 2/3 of the current sea level increase. And then the remaining 1/3 is from ocean thermal expansion, simply that if you heat water, it becomes less dense and has greater volume. There are also important regional effects, like there's some areas that have faster or slower sea level rise than the global average because of isostatic rebound of the Earth's crust from previous ice ages. or regional effects such as land subsiding. But on average, as I say, we're gaining about 3 millimeters per year, and that's growing, and the growth is mainly due to increased melting from ice sheets. So before I go any farther with ice, I want to define a few terms. A glacier is just any mass of ice that's formed from snow that has survived one or more or several melt seasons at least, and compacted into ice under its own weight and started to flow downhill due to gravity. When you think about glaciers, you typically think of a classic mountain glacier like this, the Mer de Glace in the French Alps. When a glacier gets big enough that it outgrows its topography and forms sort of a dome, then you call it an ice cap. The largest ice cap in Europe, the largest one I've ever seen personally, is Vatnajökull ice cap in Iceland. And this is an ice cap, like many glaciers in the world, that's been melting very quickly in recent years. If you get bigger still, conventionally, an area larger than 50,000 kilometers squared, which is roughly the size of Switzerland, then you call that mass of glacier ice an ice sheet. In the Earth's current climate, we have two ice sheets, one here covering most of the island of Greenland, and the other covering almost the entire continent of Antarctica. The Antarctic ice sheet is much bigger. It has almost 10 times as much ice as the Greenland ice sheet. Within an ice sheet, you have regions of floating ice that are, most of the ice is grounded, but this is the Ross ice shelf and this is the Ronny-Filchner ice shelf, which are both floating in the ocean. And within an ice sheet, it's not all moving at the same rate. There are fast-moving regions of the ice sheet called ice streams, like some well-known ice streams here that flow into the Ross ice shelf. Fast for an ice sheet means somewhere between 1 and 10 kilometers per year, which is not fast in human terms, but in ice terms, that's quite fast. And a lot of the surrounding ice is going maybe only a few meters or tens of meters per year.
The SLE, is that like how much?
Oh, sorry. SLE stands for sea level equivalent, and I'll say a little bit more about that. Basically, it means if I were to melt all that ice and put it in the ocean, that's how much sea level would rise. This is sea ice on the surface of the Arctic Ocean. It's only a few feet thick. It's ice that forms from seawater on the surface of the ocean, as distinct from land ice. When people say land ice, they mean ice that's formed from compacted snowfall. There's just one aerial picture from a colleague taken in Greenland that shows a bunch of these things all together. This is Jakobshavn Isbrae, which is one of the world's largest and fastest flowing glaciers. It flows about 10 kilometers a year, surrounded by slower moving ice that's part of the Greenland ice sheet, flowing into an ocean that's covered with sea and icebergs, and some surrounding land that has snow but is not covered with glacial ice. But you have these systems where you can see all these things together. Now, as you know, the Earth's climate has warmed by about 1 degree Celsius during the last century or so. And because humans are adapted to a very wide range of temperatures, you have to be fairly attuned to nature, I'd say, to actually notice a difference of 1 degree Celsius. But if you're a glacier, this is a huge increase. Glaciers integrate small climate changes over many years. And so nearly all the world's glaciers are retreating, and this one is no exception. This is a kind of an iconic glacier in the Alps because it's near the resort town of Chamonix, and people have been able to go and visit right up at the edge of the glacier for more than 100 years. Picture taken in the early 1900s and a picture taken recently showing considerable retreat and thinning of the glacier. And I had the opportunity to visit the Mer de Glace a year or so ago. And I will say that for someone who studies climate and thinks about it all the time, I was still absolutely stunned to see the effects of climate change in this particular glacier. Because you take a cable car up and then you take a tram down to what used to be the surface of the glacier. And when you get to what used to be the surface of the glacier, you're somewhere around here. This is where the surface of the glacier was in 1990, which is where this photo was taken. And then you look way, way down all these steps. They keep adding temporary steps every year as the glacier gets thinner. And way down here is the current terminus of the glacier. And so you walk down, and then here you are at the bottom where they've put draperies over the ice to try to reduce how fast it melts. And you look back up, and you've got 430 steps to climb just to reach where the surface of the glacier was in the 1980s. And this is not atypical of the Alps. The Alps are losing ice very quickly. The typical unit of measure that glaciologists use to talk about glacier and ice sheets is a gigaton. A gigaton being 1 billion metric tons, or the weight of a kilometer that's 1 kilometer on each, a cubic ice cube that's 1 kilometer on each side. So that's a lot of ice. That's about how much the mer de glace has lost in the last 100 years. But it is a literal drop in the bucket compared to what all the world's glaciers and ice sheets are losing. So the world's ice sheets are losing about 400 gigatons a year of ice currently. So 400 mer de glaces in a year, or more than one every day. And as a result, the world's ice sheets, Antarctica and Greenland, are raising global sea level by about 1 millimeter a year. The ocean's big. It takes a lot of ice to get 1 millimeter of increase. Smaller glaciers are adding a similar amount, and as I said, ocean thermal expansion is adding a similar amount. If you took all the ice in the Alps and melted it, which we're in the process of doing over the next few decades, you would raise sea level by only about 1/3 of a millimeter. But there's a lot more glacial ice in other places of the Earth, like the Arctic. So Alaska has about 5 centimeters worth. And all the glaciers and ice caps outside Greenland and Antarctica comes up to close to 1/2 meter. But most of the ice is in Greenland, about 7 millimeters of sea level equivalent in Greenland, Antarctica, about 7 in Greenland and about 60 in Antarctica. Of the 7 in Greenland, we're actually worried about most of that ultimately, because Greenland may not be stable in a much warmer climate than we have today. A lot of Antarctica is really cold, and a lot of that 60 meters is not likely to be lost on human timescales, but several meters we think are vulnerable to sea level rise, and I'll say a bit more about that. So Greenland, as I said, 7 meters sea level equivalent. Of the snow that falls on Greenland, when the climate was in balance in the 20th century and before, you had about half of that snowfall at some point melting at the surface and running off as liquid to the ocean, and the other half getting to the ocean in the form of icebergs, which ultimately melt. And in Antarctica, by contrast, there's very little surface melting because it's so cold. So most of the snowfall eventually flows out gets to the sea. A lot of it flows into ice shelves, and those ice shelves eventually, the ice either melts from below or calves into the ocean. Both Greenland and Antarctica are losing mass in recent years, somewhere between 200 and 300 gigatons per year for each ice sheet. Some parts of in case you've ever thought about how glaciers move, the maximum speed is at the surface. They deform kind of like molasses or a very viscous liquid, but just a lot more viscous. If they're frozen at the bed, then they're typically slow moving. But if they have water or water-saturated till at the bed, they can move a lot faster. And then so all the fast glaciers in the world are fast because they're sliding. And one of the concerns we have is that more meltwater will lead to more glaciers that can slide quickly. And what we do in a climate model is we try to add up all this together and figure out what the balance is. So you have snowfall coming in, turning to ice. Ice either runs off as liquid or or becomes afloat as an ice shelf and eventually calves as an iceberg or melts. Ice sheets in balance have enormous snowfall and also enormous calving and melting. But right now the ice sheets are out of balance, so you have more mass out than mass in, and that's what raises sea level. If you look back over the last several 100,000 years from records we have in ice cores, this particular ice core from Antarctica, you can see that carbon dioxide and global temperature and sea level are very closely correlated. In the past, temperature and carbon dioxide, one reinforces the other, and those have typically risen in tandem. But recently, of course, with human contributions of CO2, it's the CO2 that's driving the temperature increase. And sea level was, the last time sea level was about as high as it is now, it was 125,000 years ago, at the so-called last interglacial. And then you had ice sheets building up for about 100,000 years, and then a sudden loss of the big ice sheet over Canada and North America. And then over the last several thousand years, relatively steady sea level, but now we're at risk of getting another 5, maybe 10, 15 meters of sea level rise, depending on how high this goes. Sea level has been, in ice ages, sea level is lower than today because a lot of mass is locked up in ice sheets. But in the last interglacial, sea level is thought to have been about 6 to 9 meters higher than today because you lost part of the Greenland ice sheet and probably part of the Antarctic ice sheet as well. The last time that CO2 was as high as 400 parts per million, which is about what it is now, it's a long time ago and the records are less clear, but we think sea level was somewhere between 5 and 20 meters higher than today, and the climate was 2 to 3 degrees Celsius warmer than pre-industrial, as compared to just 1 or 2 degrees above pre-industrial for the time of the last interglacial. What this tells us is that the last time the climate was either as warm as today or as warm as we're likely to be later in the century, sea level was at least 5, maybe more meters higher than at present. What we don't know is exactly how long it will take for this to happen, but we can expect that the temperatures go up 2 or 3 degrees Celsius compared to pre-industrial, that we'll see a lot of sea level rise. Also, it seems that there may be a significant difference between 2 degrees and 3 degrees, which are of course important numbers because the Paris target is 1.5 to 2, but the Paris commitments are probably, current Paris commitments are probably 3 degrees at best. These are projections from the IPCC's 5th assessment report a few years ago. The sea level projections, the likely range with a low emission scenario, very aggressive emissions reduction measures is somewhere between about 30 and 60 centimeters, but with higher emissions, more of a business as usual scenario, somewhere between half a meter and a meter. There was a report on the oceans and cryosphere that came out a few days ago that raised the high level numbers a little bit by about 10 centimeters, but still roughly in this half centimeter to 1 meter range in what we can expect in this century if we keep going where we're going. It was also stated that if parts of the Antarctic ice sheet collapse, you might see faster sea level rise than this. And the reason is because of something called the marine ice sheet instability, where you have parts of Antarctica. So the picture is you've got this huge dome of ice flowing to the ocean. Here's an ice shelf. Here's warm ocean water that gets underneath the ice shelf. And this is the way the bed slopes. And because of the dynamics of ice sheets, if the bed's sloping this way, you melt ice here at what's called the grounding line. The ice retreats and the ice is deeper at the grounding line. And because of ice physics, you have a greater flux of ice out to the ocean leading to further retreat. And this will go back and back and back until the bed slope reverses. And that might be several hundred kilometers away potentially. So this is a potential instability, meaning that once it's triggered, it will go on its own, even if you stopped delivering that warm water. So this is a big concern for Antarctica, although it's very uncertain how fast that would happen once it's triggered. Another concern we have about Antarctica is we're getting warming in parts of Antarctica, leading to ponding on the surface, and in some cases that ponding can lead to the collapse of an ice shelf. This is the Larsen B ice shelf, which collapsed in 2002. So our job of Nan and I and many others are trying to model this. So we build models of the whole Earth system, including ice sheets, that we have basically Newton's laws for motion applied to ice sheets and other ice processes in our model. And our ice sheet dynamic model is one of several components of CESM that Nan talked about. So there have been big strides in ice sheet modeling in the last few years, so that now we're very good at modeling the flow of ice sheets given the boundary conditions. So this on the left is observations of ice velocities at the surface in Greenland, where red means fast and blue means slow. And this is what our model gives us without tuning it in particular, just giving it the bed topography and the amount of incoming snowfall. And we can match the observations pretty well. And we can do something similar to that for Antarctica. So we know that we've got a pretty good ice sheet model here. And now the question is, how does it respond to changes in the atmosphere and the ocean? For that, I would say the story for Greenland versus Antarctica is quite different. And this certainly has policy implications in terms of future sea level rise. In the case of Greenland, although Greenland does have glaciers that flow into the ocean and interact with the ocean, the dominant forcing of Greenland melting is a warmer atmosphere. So this shows in what's called the surface mass balance, or the net between accumulation and melting for different parts of Greenland's surface over the late 20th century, where you have gradual accumulation over most of the ice sheet, a little bit higher accumulation in the south where it snows a lot, and then melting in these narrow bands along the coast where it gets warm and melts in the summer. And when we increase CO2, in this case, we've increased CO2 quite dramatically by a quadrupling, more than 1,000 parts per million. Then we see a huge expansion of the ablation zone. And this is the state toward which we're gradually driving Greenland. And the more we increase CO2, the larger the ablation zone will be. And we think that'll be roughly a linear effect, that more CO2, more melting, less CO2, less melting. And the climate models do a pretty good job at we have a good deal of confidence in our projections of this. Antarctica is much harder because it's very hard to simulate interactions between oceans and ice sheets for technical reasons and more scientific reasons. You need a very high resolution ocean model to model these ocean flows under ice shelves accurately. But the sense we're getting from the model we use and other models people use is that this seems to be a fairly nonlinear effect because of the instability I talked about earlier. So it appears to be the case that we know the glaciers in the Amundsen Sea are retreating. That's this region here. We know they're retreating because warm ocean water is getting up under ice shelves. And we know this retreat is increasing. And what we don't know is where it's going to stop. But what we think is that there's a glacier called Thwaites and another called Pine Island, that if we dig away at those enough, we're going to reach a point of instability where after that, the retreat is maybe self-sustaining and for practical purposes irreversible. So in this simulation, we ran the model for 1,000 years. It takes about 100 years or so for the melting to get underway, but then it just proceeds inexorably until this is gone and sea level is up by about 2 meters. Whereas you may have only modest changes in the colder eastern part of the continent. So when people often ask a question along the lines of, is it too late? And I say there's very few binary outcomes in climate modeling. Typically, it's a case of the more CO2 you put in the atmosphere, the worse off you are. So the more you can reduce CO2, the better off you are. But things happen along a continuum. This may be one of the cases where it's not so much along a continuum, where it is more of a binary state. Either we keep this or we trigger its retreat and we lose that and commit ourselves to many centuries of large sea level rise. So just to summarize some other tentative answers, at least, to questions that people ask. Planners often ask for upper bounds for sea level rise, and I say probably sea level rise won't be more than about 1 meter by 2100, somewhere in the 0.5 meter to meter range, the rate we're going, unless there are surprises in West Antarctica, which we can't yet entirely rule out. And the Earth system models that we work on they're very good at most of the system, but they're not very good at these ocean changes that can affect ice shelves and ice sheets. So that's something we're working very hard to improve. And in the long term, should we hold global average warming to 1.5 to 2 degrees Celsius, as is the goal of the Paris Commitment, it's likely we'll see sea level rise of about 5 meters based on past climates, which is quite a lot, but it would be relatively slow, and it might be reversible if you could bring the temperature back down again through carbon sequestration or other carbon removal measures. But when you get up to warming around 3 degrees Celsius, climate models suggest that the Greenland ice sheet will melt entirely or almost entirely over a period of many centuries. And Antarctica, most of West Antarctica would likely melt entirely over a period of many centuries. And we're still trying to get a better grip on how fast that will take. But it looks pretty likely that we would be looking at sea level rise of over 10 meters, over 30 feet, that we'd be committing future generations to. And while this is not going to happen in our lifetimes, it's something that we're going to determine in our lifetimes whether it happens or not. So my sense is that these thresholds for ice sheets are a place where it matters quite a lot what we do in the next 30 years or so. And that by 2050, we may very well know what the future of ice sheets is likely to be. But we don't know now. It's still up to human beings to determine how much temperatures rise and what happens ultimately. So thank you.